Okay, good morning. Well, that was an empty promise about coffee. So sorry about that. But I can promise you an exciting day today with hopefully lots of very interesting and stimulating discussions. As you may remember, yesterday we laid a solid groundwork with the two keynote speeches on democratic AI and transparent AI. We had the workshops, which I thought were very stimulating and vibrant, and lots of insightful conversations. The keynotes, as you may recall, highlighted the advances of generative AI, but also the many challenges and open problems that still need to be addressed, including the danger from such things as fake images or function creep, the problems with anthropomorphizing AI, regulatory and legal issues, including the issue of having to strike a balance between innovation and regulation, accountability, as well as the, I think, largely unresolved issue of how to deal with copyrights. We had the stimulating parallel roundtable discussions on Industry 4.0, smart manufacturing, the future of research and the role of AI in it, and human-robot interaction. And we had the poster presentations, which are still available today, in case you want to have a second look. Let's proceed today with our next keynote session on sustainable generative AI and explore how AI innovation can align with our shared goals and of sustainability and environmental responsibility. Before we begin, again, a few housekeeping rules. As yesterday, the keynote speech will be recorded and broadcast online. Please refrain from taking photos or videos, as this requires the consent of the parties that are being photographed. Maybe you can use AI to generate an artificial image of how it looks inside here. And also, you have the aluminum bottles again. You have refilling stations outside, so please try to help us to reduce waste and use the opportunity to refill. Okay, it's my great pleasure to announce the speakers and the chair for our next session, Sustainable Generative AI. It's my pleasure to welcome Dr. Florence Ho. Florence? Oh, there, yes, please come up to the stage. And everybody else, please, who's in the session. I'll introduce you already, if that's fine with you. Dr. Ho is a senior researcher at NEC Corporation, has been since 2023, where she conducts research on the optimization methods for solving various industry problems and applications. Before joining NEC, Professor Ho was a researcher at ICE, the National Institute of Advanced Industrial Science and Technology. Her research interests include multi-agent systems, optimization, meta-heuristics, and traffic management. And allow me also to welcome Dr. Johannes Kirnberger. Dr. Kirnberger is policy advisor for artificial intelligence and sustainability at the AI unit of the OECD Division of Science, Technology and Innovation. He previously led the program on climate action and biodiversity preservation at the Global Partnership on AI, the GPIA, and the International Center for Expertise in Montreal on AI. Dr. Kirnberger is a member of the UNEP expert group on digital tech for circular economy. He advises an intergovernmental panel on climate change, the IPCC, on green and digital twin transitions, and serves as a guest lecturer at the Technical University of München in Germany on climate change and AI policy. Continuing, allow me to introduce Dr. Marc Duranton. He's a member of the Research and Technology Department of CEA, where he is involved in the realization for artificial intelligence, edge to cloud, and cyber physical systems. He previously worked at Philips Semiconductors and NXP, where, among other things, he led the development of the family of L-Neuro chips, digital processors for artificial neural networks. Dr. Duranton is participating in the definition of the SRAs. Oh, this is a lot of technical words I hopefully you can place, the SRAs of ECS and KDT and of ETP for HPC.
It's European organization, so a strategic research agenda for the chip GU, if you want.
Oh, thank you very much for helping me out. Yes. And he's also in charge of the roadmap activities of HiPAC on high-performance edge and cloud computing. And last but not least, allow me to welcome Professor Ryo Yokota, who's a professor at the Global Scientific Information and Computing Center at the Tokyo Institute of Technology, or it used to be the Tokyo Institute of Technology, now it's Science Tokyo.
Institute of Science Tokyo.
Oh, Institute of Science Tokyo.
Yes.
Oh, okay, thank you very much. Professor Yokota's research interests lie at the intersection of high-performance computing, linear algebra and machine learning. He's a developer of numerous libraries for fast multipole methods, EXA, FMM, for example, hierarchical low-rank algorithms, hatrix, and information matrices in deep learning, ASDL. He has been optimizing algorithms on GPUs since 2006 and was part of a team that received the Gordon Bell Prize in 2009 using the first GPU supercomputer. Dr. Yokota is a member of ACM, IEEE, and SIAM. That's a lot of abbreviations. Without further ado, I hand the baton to you, Florence.
Oh, thank you for the introduction. So first, I would like to thank the organizers for this event and also the speakers and all of you for coming today for this session. So in this keynote session, we'll address the topic of sustainability of generative AI, as reducing the environmental impacts of AI is an important matter, and it presents many challenges. And also how Gen AI can also be used to improve sustainability. So we'll have 3 presentations from different perspectives. And so the first presentation is from Johannes Kirnberger. So Johannes, whenever you're ready.
Okay, so first of all, thank you very much for inviting me to speak here and for putting sustainability on the agenda. I think especially like given the recent events of the past weeks and months, it's ever more important to keep speaking about sustainability and to keep putting it on the agenda, even if there's some sort of backlash in some parts of the world. I think it's important to keep talking about it and to keep advancing it, especially when it comes to technologies like AI. I want to talk today about the question that many people are asking themselves: can AI help save the planet? The reason why this question is relevant is because we and the planet really need some help. This is the so-called planetary boundary framework, and what you can see here, the green zone is kind of the safe operating space for humanity in the long term. And not only in terms of climate change are we way out of the safe operating zone for humanity, we're also out of the boundaries when it comes to novel entities, when it comes to biosphere integrity, so biodiversity, land system, ocean system change, and biochemical flows. So the planet is really, and not only the planet, because the planet is probably be able to, it can cope by itself, but we are in need for of some technology or something that can help us save the planet and come back from these current levels to operating within a safe space where humanity can flourish in the long term. When we, at the OECD, when we asked the G7 members for the Hiroshima AI process about kind of what do you think AI, and especially generative AI, where's the biggest impact, where can it help the most? Naturally, on kind of first place came gains in productivity. I think we've heard a lot about that yesterday. Second place was, what's on the second place? Entrepreneurship, kind of promoting science, technological innovation. That's also quite a natural place. But then came helping to solve the climate crisis, which on the one hand showed that we've been pushing the agenda quite a lot, so at least it's on the agenda of policymakers. But the big question is that actually the case? Can it help solve the climate crisis? A lot of the decision makers and kind of leading politicians of the G7 appear to think so. On the other hand, when you just do a quick Google search, there seems to be a lot of concern that AI can also help ruin the planet. You hear reports about the generative AI race has a dirty secret. There's the carbon emission problem of deep learning. Some people put numbers on it, saying that one AI model emits as much carbon as 5 cars over the lifetime. There are concerns about the application of AI, for example, in autonomous cars, kind of how much will that contribute to emissions in the long term. So there's certainly a lot of concern around AI, and especially generative AI in the recent years as well, which led us at the OECD to look at that problem, because the countries asked us to do so, because it's been coming up on the agenda. And on a very high level, I think what's been clear after researching that topic for a bit is that they're both enablers and inhibitors to our sustainability goals. So specifically looking at the SDGs, the Sustainable Development Goals of the biosphere, so climate change, life below water, and life on land, we see a lot of upside, a lot of potential enablers to kind of foster these goals, but we also see some inhibitors that run counter towards the goal of the SDGs. In the OECD, what it usually means, because we love to measure things, it means that we set up a measurement framework, which we called Measuring the Environmental Impacts of AI. And we kind of started that journey about 2 to 3 years ago, together with a global partnership on AI. And kind of the big goal of that exercise was to first develop a framework of how to think about the environmental impacts of AI. Because what you saw in the beginning, there's a lot of hype and a lot of noise and a lot of concern about it. So what the OECD loves to do, because it's a very, in a way boring but very nice way of looking at things, we like to think in terms of frameworks and then apply that framework to measure things. So what we came up with was this framework to think about the environmental implications. And generally, it really helps to think about it in 2 ways. One is the direct environmental impacts and the indirect environmental impacts. The direct environmental impacts mainly relate to the physical infrastructure on which AI itself runs, which sometimes can be easy to forget, because AI can be perceived by a lot of people who are not who don't work in that field, but something intangible, something almost magical, something that sits somewhere in the cloud, but in reality it's really it's grounded in physical infrastructure and heavy physical infrastructure. And that physical infrastructure has impacts along the entire value chain. Starting from production, you have environmental impacts from raw material extraction, to assemble and manufacture the components, then you ship them, you assemble them, you build the data center itself, and then the biggest impact is in the operation phase. That means simply running the data center, running the processors, which takes a lot of energy. It has a big water footprint as well, and both of those have an associated carbon footprint. At the end of the day, you need to hopefully recycle. In reality, not much is recycled. The number is something close to 85% of the electronic waste is not recycled, but it ends up in landfills, mostly in developing countries. So another huge environmental impact kind of at the end of that life cycle. I'm sure we'll hear a lot more about that aspects from our speakers afterwards. The other big thing, and that's where the potential impact is even higher, but it also gets much more difficult to actually measure it, is on the indirect environmental impact side, which means applying AI to certain use cases, kind of actually running AI for different purposes. And again, here you have a lot of positive and a lot of negative impacts. On the positive side, broadly speaking, what AI is great for is optimizing existing systems, making existing systems more efficient. That can be in energy, that can be in transport, that can be in agriculture, that can be in industry, that can be in any field, any sector that has where you have a large amount of data. You feed that into an AI and it helps make your existing system more efficient, which in turn translates to energy savings, emission savings, so on. The second big positive potential for impact is in environmental modeling and forecasting. So the the existing models that very often run on high computing infrastructure, that can be improved by AI. I'll show you some examples later. But AI is really useful and is already applied in modeling and forecasting, which in turn helps with disaster prevention, etc. And then a third is, generally speaking, on mitigation and adaptation. We've heard a lot of examples yesterday how AI can help with scientific discovery, which is also highly relevant for sustainability when it comes to renewable energy technologies, when it comes to new mitigations and adaptation strategies, when it comes to new material science, which in turn can help with a lot of the problems that we encounter in sustainability. That all on the positive side. On the other hand, there are also a lot of negative impacts, and that's really something I want to emphasize, because very often when you hear about the discussion of AI and sustainability, you hear about kind of a dichotomy between negative impacts on the infrastructure side and positive impacts on the application side. But there's a third element, which is the negative impacts on the application side. So of course, AI being a tool that can be applied to a bunch of things, you can apply AI for oil and gas exploration. You can apply AI to make kind of consumption patterns worse, to make people buy stuff they don't need. So applying AI to sustainable use cases does not only mean that you apply it for very environmentally beneficial cases, but there's a lot of downside on kind of using AI to further existing business models that are fundamentally unsustainable. Bit on the positive side, just three really high-profile examples. There's on the top left, that's called the Destination Earth project from the European Union, which is a project to develop a digital twin of planet Earth. That's also going to take a few more years because it's quite ambitious. But essentially, the idea is similar to what you may know from digital twins of factories. So you have a kind of digital representation where you can model certain developments and then apply it to the real world. Same idea, but for planet Earth. So that's going to be pretty exciting when it comes out. But again, huge resources to develop that model. The second one is Climate Trace, which uses satellite image and AI to trace the high emission sources again on planet Earth. It's really cool. I highly recommend going on that website because you can zoom in like directly into your city, into your neighborhood, and see where the big emission sources are. And the third one is using AI to make AI itself more sustainable. What Google calls carbon-aware computing. So they're shifting computing workloads depending on wherever they have the most renewable energy available. So yeah, a lot of these applications. Two more, specifically on generative AI. One is called Chat Climate, which is basically ChatGPT, but exclusively trained on the latest IPCC reports. So again, I highly recommend that if you ever want to have a discussion, an informed and expert discussion on sustainability, use Chat Climate, because that's kind of a companion, but a highly knowledgeable companion that knows all the IPCC stuff. On the right is another example that's a startup from Munich called Tanso, which uses generative AI to help companies with their carbon footprint reporting and their sustainability reporting, which again helps companies comply with regulation, but also frees up a lot of time to do the actual sustainability work. On the downsides, and that comes back to a bunch of the headlines we saw before. The computational needs of advanced AI models are growing exponentially, and they have been growing exponentially for quite some time. And recently, they've already grown exponentially in the pre-deep learning era, but since around 2012, 2015, the deep learning era, that has seen other acceleration, which naturally, when you just look at that chart and you know how much energy that takes, raises a lot of concerns. And coming back to the harmful sectoral applications, AI can be used for environmentally harmful applications, be that in exploring new oil and gas fields, be that in inducing a lot of demand. That being said, measuring the actual environmental footprint, and here we're only talking about the direct environmental impact, so how much energy, how much water, how much emissions does it take to run AI models, is highly complex. On the left side is a by now quite infamous work from 2019, which came to the conclusion that training an AI model, that's already a bit problematic because there's not an AI model, but let's just put it that way. Training an AI model takes about 5 times as much as an average US car during its entire lifetime. That study was highly publicized. There were a lot of reports about it because it's quite a big figure. Then Google was like, wait a minute, that seems a bit high. Let's run it through our data centers. Let's run it through our numbers. And what Google found is that the execution time that the researchers had estimated was off by a factor of 17,000. The costs were off by a factor of 50,000, leading to the CO2 estimates being off by a factor of 120,000. So instead of 5 cars over the lifetime, I think it was something like 0.000004 cars over the lifetime, which, as you can see, is quite a big difference. Not necessarily because the left side was wrong in their calculations. They just had to use averages, because what's really hard in AI, or in kind of estimating energy costs and environmental costs of AI, is that the sector at the moment is highly intransparent. So the researchers have to go with kind of averages in terms of computing infrastructure, in terms of the energy mix of the grid. So that leads to these kind of big differences in estimations, and that makes the entire conversations about AI and sustainability very difficult, because you're relying on either averages or it's just up to guesswork. The big question, and that has also taken us by surprise, because our report was done before generative AI was kind of really taking off. The question is whether generative AI changes our entire analysis. Already the projections, that's from the International Energy Agency, is that data centers in terms of energy use is going to significantly jump in the next couple of years. Now on top of that, and already that is a bit of AI, it's hard to say which percentage exactly, but already that entails a bit of AI. But then on top of that are going to be dedicated AI centers, so-called AI factories, that have an entirely new kind of architecture dedicated for AI training, and that might take another step in increasing the energy consumption. The other big question is whether training or inference is going to be the dominating factor. At the moment, again, hard to say, because it's mostly a trade secret, but you can say something like 40-60, 50-50 in terms of energy consumption of training and inference. Now the assumption is that as generative AI becomes more prevalent and gets integrated in something like a search engine, then the energy cost dramatically shifts towards inference, because you just have a lot of instances of using the generative AI instead of training it. So that's the other kind of wild card in the assumptions. Fundamentally, what the big question is whether the efficiency improvements of computing are going to keep up with the energy growth from computation. What's interesting is that over the past decade, over the past 15 years, the total energy consumption of data center has been almost flat. Not entirely flat, but almost flat, especially when you look at how much internet users, how much internet traffic, how much computational workloads have increased by several orders of magnitude. So far, the efficiency increases have really limited any significant growth in data center energy consumption. But again, the big question is, does generative AI change that? And we'll hear a lot about from the experts here. Is it possible to, again, keep innovating and keep improving energy efficiency, so that the energy requirements don't explode? A quick word on kind of my daily work, which is governance and policy. The international AI governance landscape, and I'll bring that back to sustainability, is highly complex. You have a lot of different players, a lot of different formats. The OECD and GPI being one of them, but continues with the G7, with the G20. There's a lot of work on the UN level. UNESCO does a lot of things. So there's a lot of different initiatives to keep in mind, and specifically on sustainability, there is some early steps, some early signs that sustainability is on the agenda of all these initiatives. Just to name 4 of them, in the AI Act, there's specific language on sustainable AI, on KPIs and references for the SDGs, and on kind of a mandate to promote sustainable and environmentally friendly development of AI. Same goes for the Hiroshima process and the Code of Conduct, which again has language in it to address the world's greatest challenges, such as the climate crisis. Same goes for the executive order, although we'll see where that goes in the next couple of months. But it does have language on catalyzing AI research that's really focused on the positive applications, on the upside of using AI, again for climate change and resources. And finally, the Bletchley Declaration last year, which also had China in it, again had a reference on clean energy, biodiversity, climate, and the UN SDGs. So you can see that within kind of these early AI governance, AI policy initiatives, there is a mention of climate. But at the same time, to be very fair and to be very honest, that is very high level. So the most ambitious in that form is the EU AI Act, but even that only has, it's largely not mandatory, it's largely voluntary for AI developers. There is the idea that very high risk systems will also need to address their energy costs. But again, the KPIs have not been set. There's a lot of work now on standard and measurement development in the ISO, in the IEEE, Senelec on the European level does a lot of things. AFNOR in France, and the French government is also very behind it. There's the upcoming AI Action Summit, right? AI Action Summit is the name, yeah, in February. And sustainability and transparency on sustainability is one of the key kind of agenda points for that. So it is kind of early days in developing metrics and standards, but it's urgent because you've seen what happens when you don't have transparency. Then you have kind of cherry-picked data, you have a lot of anecdotal evidence, but to really understand the problem and to be able to inform decision makers, policymakers, technology companies on how to make AI more sustainable, you do need that kind of standardization, measurement, comparability between the different systems. So yeah, it's early days. I hope that gave you a good overview of the different dimensions of sustainability, and looking forward to the discussion and your questions. Thank you.
Thank you very much. So the next presentation is from Marc Duranton. So looking forward for your presentation.
So first, I would like to thank the organizer for inviting me and for the audience to be here, because we have a very tough competition, because at this very moment, Jensen Huang, the CEO of NVIDIA, is making a keynote here in Tokyo. So thank you to be here. So my presentation will be going more into the hardware part. So thank you, Johannes, for setting the scene. And first, I would like to give you a short story of hardware for neural network. So the rebirth of neural network was done in 2012 with the work of the team of Hinton that just wins the Nobel Prize. Basically, they make an architecture called CNN that break all the record into image recognition. Basically, they make a neural network with 60 million synapses. So this was a breakthrough, and the hardware that were done before, so this was the hardware that I made in the 90s for neural network, was not able to do that. And for the training, they use NVIDIA GPU, so it's why NVIDIA now is a leader in hardware. So for training this 61 million parameter, they need 262 petaflops. So peta is 10 to the power 15 floating point operation per second. So the second key element in the recent AI history is a paper from Google about transformers. So that was the start of all this boom on generative AI. So this paper was in 2017, and as you see in their summary, one of the drive was to be able to parallelize and to reduce the training time. So hardware consideration was one of the drive for them to invent this architecture. So just 1 year after, a small startup called OpenAI make their first model called GPT-1, so a generative pre-trained transformer. So it took 1 month on 8 GPU to train their GPT-1. 1 year after, they make GPT-2 that's required 88 times more compute power. After, they go to GPT-3, that is 213 more time compute power for the training of GPT-3. And GPT-3 was basically the root for ChatGPT that you know started the big bang into generative AI. And for GPT-3 to GPT-4 is still an increase of 65 times more compute power. So if you see the story in very few years, so basically in 5 years, it was an increase of nearly 1.2 million times in compute power to train this. So if we compare to the first AlexNet, so the 61 million parameter, to GPT-3, which was 174 billion parameter, so it needs 323 not petaflop, but zetaflop, so it's 10 to the power 21. So that's, again, 1 million times more floating point operation. And we really see it's because of the hardware that was able to increase their performance that they were able to scale, and we are now with the story of generative AI. But there was also another drastic impact of this is improvement of energy consumption of the hardware. So here is GPU. So in 8 years, we were able to reduce by a factor 350 the energy consumed to train a neural network. And you could see that before 2018, it was not practically possible to train big neural network because the energy consumption would be really enormous. So it was because of this increase that they were able in 2020 to train GPT-3 that basically roughly need, well, equivalent in fact of GPT-4 could be 40 gigawatt hours of compute power. And again, the improvement of energy efficiency allow them to train GPT-4 with an affordable cost of energy. So, of course, this big company, they claim that it's for to be green, to consume less energy, but it's mainly because of the cost of electricity. So, really, the cost of energy for training is really the limiting factor for all this generative artificial intelligence. And so I will also take the same example as Johannes with this famous paper from MIT that they say that training a neural network could use five US a car. So this was a paper from 2019, but with the same numbers as they took in the paper. And I agree, we will see later that Google has other number. So you say that, okay, for GPT-3 in May 2020, it will cost about 502 tons of CO2 to train a model with 174 billion parameter. But only 2 years after, Meta trained their Opt model, which was the same size, 175 billion parameter, with a reduction of CO2 by 7.2. On Bloom, which was also in its version of 176 billion parameter, again get a reduction of nearly a factor 3. So with the same kind of measurements, so we see a decrease on CO2 emission by 21 in less than 2 years due to the improvement of hardware. So a small word about Bloom. So Bloom was a foundation model trained with a big collaboration of scientists in Europe. It was trained in France on the Jean-Zay supercomputer. And its small footprint was mainly due to that the computer is mainly powered by nuclear energy, and the generated heat is also used for heating the campus. And we should notice that Bloom was available a few months before the big boom of ChatGPT. Okay, so this is the state. So now, how we could, from the hardware point of view, make more sustainable generative artificial intelligence. So as you see, so again, for those that are not in the Jensen 1 keynote, I use some of his slides, so I'm sure he will present this also in the other meeting today. So you see that in 8 years, there is 1,000 times increase in performance of hardware for accelerating or for computing a generative AI. So this was due not only to the Moore's law, so to the technology improvement, but also for the fact that we changed the coding from floating point 16, so 16 bits to code the operation to 4 bits, but also to the architecture improvements. And it's basically what I will deal here. So just to tell you the basic drive for this is that the more you specialize, the more you gain in energy. So between a CPU and a GPU, for the same operation, so you gain nearly a factor 10 in energy efficiency. Of course, GPU is more general purpose. It can do more things than a CPU could do more things than a GPU. But for the thing that the GPU could do, because it's more specialized, is more efficient. And if you go one step further with even more dedicated hardware, so you could gain again a big factor. So you see here that going from a CPU to a GPU, you gain a factor 150 in energy efficiency. And to go back to the slide of Johannes about Google, I will take another example. In 2017, Google took the constatation, so that was just the start of the voice recognition and interacting with voice. And they took the constatation that if their customer use Google Voice only 3 minutes to make a search per day, they will need to double the number of their data centers. So we say, well, it's not possible. So we need to define and to make a more specialized architecture. And it's why Google started to make their own chip called TPU. So they make a full generation. So I think we are not now at the 6th generation of this. So this is a big machine. So this one is about 12 petaflop for more than 400 kilowatts. So this was in 2017. So if we compare the performance of hardware 5 years after, so here you could see that for the same performance, you could use only 5 chips of the H100. So you see that with this, instead of having a big machine consuming more than 400 kilowatts, this could be done for the same load with only 6 chips with a far more lower footprint, both for making the system, but also for energy consumption. And just one slide also to say that from one generation to the other, so again, this slide from NVIDIA, so that you don't regret not going to Jensen keynote, you could see that they go basically by nearly a factor 10. So that used to take 7 days to train on the A100, took only 20 hours to train in the H100. So you see, really, the hardware, due to specialization, optimization, could be really improving. And of course, you have the rebound effect. So the more you offer compute power, the more scientists and companies want to increase the size of the system. So it's why us, as architects, need to be even more better in improving the energy efficiency. But we also see another trend. It's the use of, instead of gigantic a model like GPT-4, using more specialized, smaller model. So these are models fine-tuned for particular application that could be quite good for this range of application. You could see here that's a model now with about 10 billion parameters has a similar performance of ChatGPT of 2 years ago. So on this small model can now run on not only on a cloud on the server, but on your devices. So this is typically what Apple is doing with their Apple Intelligence. So it's quite an interesting approach here because they are using neural networks. I don't enter into the detail. They are also using some more classical approach to pre-process the data, and it's some kind of agentic AI. I will go later, because if the network on your device are not powerful enough, they could ask to the server to do some other tasks. So it's really collaboration between the local devices on the cloud. And just I take an example of a chip that is present in some of the Chinese smartphone. So this chip is able to handle network of 7 billion parameter or even 13 billion parameter with compression. And I choose this one because it's also able to make a fine-tuning of neural networks, so it could adapt the neural network to your particular data set on device, so locally with on your smartphone. So we see that processing at the edge take less and less energy. So here you could run a large language model on your computer. So here I was using one model of, I think this was a 24 billion parameter on my Mac Mini that consume less than 20 watts. And Apple is also claiming that the new generation of Mac Mini is carbon neutral. So some kind of greenwashing here, but they indeed reduce the energy consumption, the packaging, the transportation, everything that was basically presented in one of the slides of Johannes. If you go if you go to more specialized devices, like the one that you could have in your home, so it's basically 3 to 5 watts. If you go to even more specialized devices that are able to understand 200 commands or 200 sentences, basically for home automation, so it's even a milliwatts. And at CEA, we were working in this development of ultra-low power chips. So this is a chip that we developed for keyword spotting. So keyword spotting, you know, is when you have an Alexa device, so it needs to listen all the time until it's heard Alexa, and when it's Alexa, then it could trigger and power on the big neural network to make this. But that recognition needs to be constantly on. So that was, it need to consume very less energy. So we have a system that consumes only 12 microjoule, so it could be powered by year on a Bhutan cell battery for this. And it's also able to do that for vision, so detecting people entering in the room or a cat or something like that, just to trigger the big artificial intelligence. And this was an award at the embedded work, and we demonstrate this at CES 2023. And our last devices is the one that you could also see running here. We demonstrated at CES 2024, and it's again this idea of more specialization. So basically, here, most of the processing is very specialized to extract the feature of the image. Then we have only 5 to 10% that are really programmable to adapt to the various functionality, like autonomous weeding system, pest detection for tomatoes, or drone control. Or here you could see some object reconstruction. So this is processing a high-definition image with only 23 milliwatts. So it's not megawatts, it's milliwatts. So again, it could be powered by battery for quite a long time. So the next step also is, so you perhaps heard about neuromorphic computing. So it's basically using different information coding, so using computing only when information change, also using the sparsity of information. You don't need to send always information. You could code information in only 1 bit, and you could use physics to make computation. So typically, the basic of neural networks is a weighted sum. So here you could see, you could use Ohm's law to make the products and Kirchhoff's law to make the addition. So very minimum hardware. So here could be very efficient hardware. So again, here with CEA, we have a collaboration with TDK on exploring this new idea, and we win also at CTEC last month. So an innovation hardware. And in preparation to the next session that I will be hosting, I will talk rapidly about agentic AI. So as it was said, inference is demanding a lot of energy. So some companies say that OpenAI need nearly 7 times more GPU for inference than for training. Why? Because they have 200 million users per week, because users are using a lot of this system. So again, these companies are making dedicated chips. So you find Groks. So AWS are making a special chip for inference. So they call it Inferencia. So they also make a dedicated chip for training called Trainium. But what is the next step is, even in the algorithm of the neural network, you could specialize part of the neural network. So the first one is called mixture of experts. So inside the big network, you will specialize part and will activate only the parts that are relevant to your question. And if you go to one step further, you could go to having specialized agents, specialized smaller networks that are specialized in special function. So that's called agentic AI. And agentic AI is the next big thing. So so you see that, okay, mixture of expert was in OpenAI, and you see here Eric Schmidt is saying that this is the future. Of course, Marc Zuckerberg. I'm sure today Jensen Huang is saying the same thing, and this is the key drive for tomorrow, because this could be distributed, and that is basically the way where you could play with sustainability, in the sense that if your smartphone is not powerful enough for the next neural network, it could ask to your laptop or to the smartphone of your wife to do the other tasks. So this network of agents could work together. So that means that instead of needing a big data center, you will have this thing. So I think it's one way for more sustainable functionality as well. So just to conclude, in the past, everything was done in the cloud. So now training is still done in the cloud, but inference on some systems are done locally, like for self-driving car. Of course, it's need to detect pedestrian on the car and not relying on the communication. And we see the future will be more of this federated, distributed of a smaller agent working together to make more global tasks. So this is a more global framework, not only for AI. So in the case of AI, it's called agentic AI, but there is more global dimension in this new architecture that we promote in the IPIC vision. So you are welcome to download and play with this. So here during the lunch break, you could see the hardware here making object recognition in real time. Thank you very much.
We'll move to the next presentation from Ryo Yokota. So whenever you're ready.
Thank you for the introduction. I'm Ryo Yokota from the Institute of Science Tokyo, and today I will be talking about the sustainable development of GenAI in Japan through continual pre-training. So it has been mentioned in the previous presentations that the amount of compute spent to train these large models has been increasing rapidly. And the rate at which it's increasing is actually much larger than the sustainable rate. And so if you look at this figure, you see that roughly, if you draw an average trend, the amount of training compute that is used to train these large models in the deep learning era. So this plot, like the previous one shown, is only showing the deep learning era after 2012. And this slope is roughly 10x every 2 years. So we know from the hardware trend that Moore's law tells us hardware is improving roughly 2x every 2 years. And so the remaining 5x is coming from simply expanding the scale, basically paying more for the price of the hardware and also using that much more energy. And so the cost of training one of the largest models at the moment in 2024 is already in US dollars, $1 billion. And if the 5x is needed to sustain this effort, then you see the cost skyrocketing all the way to 2013 at 125 billion. And so this is not at all sustainable. And you can see that this trend will not continue. It will plateau somewhere very soon. But the interesting thing is these large training computations are done only by very few companies. It's only the top few companies that are doing this. And so the rest of us, what can we do? This is another question. Especially in Japan, there has been a lot of investment recently in AI hardware. For example, AWS plans to invest 2.26 trillion yen into the Japanese cloud infrastructure by 2027. Also, Microsoft is planning to invest 2.9 billion US dollars into AI cloud infrastructure in Japan. This is also a huge investment. Also, OpenAI, one of the top companies that are producing AI technologies, is introducing a Japanese branch. Their first office in Asia, actually. Also, SoftBank, a Japanese local company, is investing nearly 1 billion in AI. And actually, at the NVIDIA event happening now, Masayoshi Son, the CEO of SoftBank, is having a fireside chat with Jensen Huang, the CEO of NVIDIA. I think it's happening at the moment. And so this is a huge push in AI in Japan. We also have a new startup called Sakana AI. These are former Google researchers. One of them is actually the author of the Attention is All You Need paper, which is a very influential paper that proposed the transformer architecture. One of those authors is in Japan doing a startup now. And they have a huge valuation and a lot of investment from the US has been invested in Sakana AI. Of course, if you want to train these very large generative AI models, you need access to a lot of text. And so when you say you want to build a Japanese model, you need a lot of Japanese text. And when I say a lot, it means basically all of it that's available on the internet. And if you look at the content, internet users on the internet that speak Japanese, they're 4%. If you look at the available Japanese content, it's 5%. And so the ratio is roughly similar. It's 4% versus 5% for Japanese. This is very different from Chinese, where you have 23% in terms of the population using the internet in terms of the Chinese-speaking language, but the actual content available in Chinese is 3%. And of course, English is the dominant language on the internet, and therefore that's why these models that OpenAI trains is dominantly, primarily trained on English. And we see this primarily English trained model to be not so useful in some cases when you need Japanese cultural context or some historical context that is not sometimes available in English. So we have two major efforts. I'm going to talk about two efforts today. The first one is called LLMJP. So LLMJP is a huge consortium in Japan. This started around May in 2023, last year. And it's a consortium of many different universities. Probably it has grown much larger than what's shown here. Because it's continuously growing, I do not have the complete list of industrial partners or laboratory partners. So note that this is not a complete list, but you can see that there are many, many companies, universities, and national laboratories participating in this. And we are training a very large model, equivalent to a GPT-3 scale, which has about 170 parameters. And we've trained both on Japanese and English. The English data is available. There's a lot of clean English data available to the public, but Japanese not so much. So one of the major efforts is to collect enough Japanese data here. And the groups are split into people who crawl the data, crawl the internet for data, and then clean them. Also collect data from papers and books, which are naturally clean data. And also people who work on the neural net architectures, also pre-training. And I'm not sure how this works. It doesn't show the... But anyway, so there's a group that... Yes? Should I use a mouse? No, I don't. I want to point. The laser pointer is not working. Yeah. But anyway, so I'll move on without a pointer. But I hope you can see in the middle we have these different groups that work on instruction, safety, evaluation, and safety. And unfortunately, we don't have a group working on sustainability. Okay, this is not typical for these large LLM efforts to have a dedicated group for sustainability, and maybe this is something we should work on. So the next few slides will be a little bit technical. I just want to show you that it's not easy to train these large models, and I'm going to show you some failure cases that happened during this huge effort involving so many people. So we started out with small to medium scale models, 1.3 billion parameter and 13 billion parameter models. And these are what's shown here is the loss, the training, what we call the training loss, which is the objective function that we want to minimize. So when this gets lower, basically the model is getting better and better. And so in the beginning, we have a very large value of the train loss, and this decreases. And then at some point, it stops decreasing very rapidly, but that it looks like this because it's plotted against the number of steps. And so if you run for many, or actually an exponential number of steps, this is actually, it keeps decreasing. And this is what's called the scaling law. You can scale the training to train on much larger data, and the model keeps improving monotonically. It does not plateau so far. But for these size models, it's very stable. And you can see these different colors are when we restart the training. So because this training takes so long, sometimes months, we take a checkpoint and then restart from these checkpoints. So that even if the hardware crashes, we can do the training from these intermediate checkpoints. And then once we went to the GPT-3 scale, the 175 billion parameter model, we had this case where the loss started to increase. And we restarted with a lower learning rate, and yeah, we tried everything, but we just couldn't get it to decrease anymore. And so when this happens, you cannot train any longer. And so even though you're spending a huge amount of energy, and this is not very good for the environment, I mean, it would be nice if you were able to create something useful, but this is all happening for nothing, right? And so this is the ultimate case of wasting resources, where you fail to train. And I believe this is happening in many places around the world at the moment, because everyone's trying to replicate this technology. And we are not sharing these failure cases. And so we are redundantly failing and using all these computational resources, which is, I think, consuming more energy than these major companies at the moment. So the important thing is to share these failure modes and also what worked. Another case, so this is our second trial of the 170 billion class model. This time it's 172 instead of 175 because we changed a little bit the model architecture. So we are training on, I'm not allowed to disclose the number of nodes, but on many GPU nodes, each with 8 H100 GPUs from NVIDIA. And so one thing that happened in this case, so the training loss decreased quite nicely. We didn't see any trouble in the training loss. But when we started to evaluate on the actual use cases, on the benchmarks like translation, human understanding, or math, all these different benchmarks that we evaluate these models on, we saw that this large model was performing even worse than the smaller models, and we tried to see what was wrong. It actually turned out to be this red number shown here. So this is a very technical thing, but we use, for the optimization method of these large transformer models, we use a method called ADAM. And there's a specific value called epsilon. This is a parameter that you adjust. And this was set to 1e minus 5 because it said so in the Llama 2 paper. They said it should be 1e minus 5. And we followed this. And oh, thank you. And this number here was actually, I think it's incorrect. I think it was a typo in the paper. But this cost us so much. Actually, when you experiment with the proper value of 1e minus 8, then the evaluation scores increase like this. But anything that's trained, a 13 billion, 70 billion, or 172 billion parameter model trained with this wrong number just does not give good performance at all. And this is the actual excerpt from the paper itself. It says EPS, 10e minus 5. And I contacted the authors, they did not respond. I'm pretty sure this is, because this is a very famous paper that everyone is following, this could be happening in many places, and people don't disclose their failures. So again, this is like a silent catastrophe that's happening in many places around the world, and we were not an exception. The second effort is somewhat a more smaller scale effort. This is between, well, now our institute is, instead of Tokyo Tech, it's called the Institute of Science Tokyo because we merged with a medical school. But anyway, it's between mainly our group and Professor Okazaki's group at our university. And we use the resources at AIST. This is called the ABCI supercomputer, which has many GPUs. And so in this collaboration, we are taking a slightly different approach. So this is called continual pre-training, which is much more efficient in terms of the amount of resources it requires. The reason why it is more efficient is because you take an already pre-trained model, something like Llama from Meta. So Meta spent so many GPU hours and so much energy and so much cost training their model, and fortunately, they open their weights, which means you can continually pre-train from them. For example, if you want the Japanese capability to increase more than their original model, you can actually add a lot of Japanese data by continually pre-training. And of course, there are certain issues. The disadvantages are we don't know what data the model was trained on because we have no control over it. They just disclose the weights to train on. So the advantage would be the transparency. If you want to train from scratch, you have transparency, but the disadvantage of training from scratch would be the enormous data and computer resources. So you could either be green or transparent, but you can't have both. This is sort of the dilemma that we face. And one good trend is that there are many people trying to do this kind of open weight approach. So it's not just Meta that released the Llama model. Mistral, this is a French company, they release also their weights, and this is an open approach. So we can also continually pre-train from their model. QN is a model trained in China. This is currently the strongest model, and it's very competitive with the OpenAI and Google models. So China now is leading in sort of the open area, and also it's competitive with the closed models. But this means the open community is catching up. So it's not just these closed companies that have all the special knowledge to train these models. The technology that is in the public is actually becoming competitive for the current benchmarks that they are benchmarking on. Of course, for more difficult benchmarks, the story might be a little bit different. So one of the reasons why we want to train our own Japanese model also exists not just in the Japanese knowledge, but also this token efficiency. So in normal plain English text, if you say something like this, so characters not in the vocabulary are broken down into UTF-8 bytes, consuming as many as 3 tokens per character. This is broken down into these colorful tokens and fed into the network. When you do the same thing in Japanese at the moment, this has the same equivalent sentence, equivalent meaning, and this is broken down into much more tokens. It consumes about 60 tokens. OpenAI or Google, they charge us per token, which means they charge us 3 times more to say the same thing. For the same question we ask, we get charged 3 times more. We wanted to somehow make this more equivalent. And so we used our own tokenizer, which sort of brings this down 3x so that we can use efficiently even Japanese text. But to do this, we had to retrain with a lot of Japanese text. And so we ended up taking, a lot of, this is like 63 billion pages from the internet. We filter that with language, extract certain parts of the text according to, these are standard techniques now to filter all the data. So actually, when you hear that we are training on all of the internet data, you might think we are training on very poorly written text. But this is key. You filter so that you only train on high quality text and high quality Japanese text in our case. In the end, we have, so this Tokyo Tech AIST Swallow model, the name of our model is Swallow. This is actually generated by AI, a swallow interacting with a llama. So we take the llama model, which is open, add Japanese, continual pre-training, and then we call this the Swallow model. And on Japanese benchmark scores, we are better than the original model, of course, and also other models trained in Japan. But the English score decreases a little bit. But the decrease of our model is not as much as the other Japanese models. So and currently we have these benchmarks, and our model is currently here, probably the second best one in terms of this benchmark. So it depends on what you benchmark on. So sometimes we are top 1, sometimes we are top 2. And this is the comparison with the Chinese model QN, which also speaks pretty good Japanese. And depending on depending on the task which you require it to solve, we have certain tasks that we are stronger than this model, and certain ones we are weaker. So you have a huge variety of benchmarks that indicate different trends in the different models. So this is all very complex. You cannot just say, just because we trained our own model, we have something better in Japanese. It depends on what you use it for. So in conclusion, this is a summary. Training of larger models is more unstable than smaller models, so it's not easy. Some people think that if you have enough GPUs and have enough money, anyone can train this. This is not true. You need good people that have experience training these. Otherwise, you will lose or waste so much energy and money on this, because you find out too late, and the consequences are huge. Also, continual pre-training on non-English languages is an effective approach. This is not just for Japanese. We did it for Japanese. This can be done for, well, I know that it is currently being done for French and German, and also other languages in Europe, as well as other languages in Asia as well. So Singapore also has a strong effort in this direction too. And so this approach, because it leverages all the resources that are already consumed by these companies anyway, and adds a little bit more training, it's a slightly more sustainable approach. Yeah, we have presented these results at the recent conference that was held in Philadelphia in October. If you're interested, you can refer to these papers for details. Thank you very much.
Thank you very much. So we just got 3 very interesting presentations about sustainability of generative AI. So they complement each other well. The first one was on the policy aspect, and the second one was on the hardware aspect, and finally on the software aspect. So now we have just a few minutes for a few questions, and then after that we'll take the questions from the audience. So I will maybe a first question, because Leo just presented specifically about the Japanese kind of a use case in Japan. So maybe the first question is how generative AI could be adapted to the cultural differences between different countries in the laws or the languages, like in Rio's presentation. Could you say something about that?
Yes, sure. So in my presentation, I only touched upon the language aspect, but there's also the cultural aspect in continually pre-training. So all of these large language models, when they are first trained, they do not follow the instructions very well, and they also do not behave in a way that is safe. And so we do an extra post-training phase where we actually feed it in some question and answers, which we sort of created by humans in a sort of preferred and safe manner. So we give it examples of what the correct way to answer these slightly sensitive questions may be. And this is done in very different ways in the different countries. And it sort of reflects the local culture, because there are certain cultural norms that differ between the countries, and this phase cannot be relying on just a single company in the US sort of dictating how these models should be aligned to human values. There are different human values. Of course, there are different views within the country, so each country could have multiple of these models. But at the moment, the approach is to sort of refuse to answer these sensitive questions. And sometimes overdoing this makes the model very unhelpful, because it's actually these sensitive cases that we sometimes need the help of these AI models. And so I think it is necessary to continue this effort for each country to do this post-training phase, at least, which does not require as much computational resources as the first pre-training phase. So this is both within our reach, and I think it is a sustainable thing to do. And I think it is a very necessary thing to do, to sort of keep our AI somewhat sovereign. There's a keyword called sovereign AI, which NVIDIA is using today to promote their hardware. But of course, if all the countries need to do this, they need to buy the GPUs. So NVIDIA is also backing this effort up. But from a moral perspective, I think this is a very important endeavor to keep these models somewhat local capable, but still aligned to our local cultural values. And this is important for Japan. So we are continuing to do this, and we plan to continue as well.
Thank you. So do you have any?
Yeah, just to add to the comment about sovereign AI, because that's something that, like on a global scale, is very much discussed, and because we at the OECD we also track kind of compute resources on a per country basis, which is also very complex. But what is clearly emerging is that there are kind of different tiers of what access countries have to advanced compute. You can think of it as a kind of global. There's a big compute divide, and you can think of it as like there's a compute global north, a compute global south, and then that's terminology from University of Oxford, which we have been tracking it, a kind of compute desert. So in a way, there's a huge disparity between access to kind of advanced compute and to the most cutting edge chips from NVIDIA. So in addition to the culture and language differences, many countries do not have at least to like run these very large models, they don't have the ability to access the compute resources in the first place without even starting to think about culture or language. So that's a really important aspect, and that's I think also from a geopolitical point of view that comes up a lot, and that concerns a lot of countries who want to be sovereign in a way. And if that's the technology of the future, then you want to be able to control at least some parts of the value chain for yourself as well.
Thank you. Any comment?
I think this is also very important to adapt to the different culture and even to the different communities, because you could have also subcultures that are not represented and didn't have enough access to compute power. So again, in this vision of agentic AI, this could be also a way to train smaller model even on I don't say a personal computer, but at least at the level of small organization to fine-tune them. And the point is that if they work in collaboration, they could really have the more than the sum of each of the network together. So large LLM didn't have a representation of a word in Japanese, in French, and or in English or in German. They have some common representation internally of a concept. So we need to have perhaps this small specialized model to make the interface with human to the more global knowledge. So again, we could perhaps push in the future, so I know that it's a version for the future, going to more distributed, federated AI that could work at countryside or continent side. But for example, when I am coming here, my personal AI could discuss with the AI here, and they could exchange information. And for me, the interface will be in French or in English, but it could be able to communicate with Ryo's AI in Japanese. So then we could have through this agent more personalization of the system.
Okay, thank you. We have time for one.
Yes, thank you very much. We have quite a few interesting questions. I summarize a little bit so that we can squeeze in more. I think there were two that are somewhat related. Relating to the fact, first of all, Germany, Japan, France, electricity prices are fairly high. Plus, we'd like to have companies use renewable energy, which is maybe even more expensive. So what can be done also on the political side to fulfill these objectives to keep AI development competitive in our three countries?
So I can talk from the hardware point of view. Again, it's also a link to what Ryo was saying. Of course, we could train our foundation model with big set of GPUs. So in Germany, in France, and in Japan, we have this big supercomputer that could be used here. But we see now that if you really want a democratization democratization of AI, inference is becoming more and more demanding. So we need perhaps to have local actors that work perhaps on more specialized hardware that are more efficient for this. And so there are companies starting working in this definition. So perhaps you have heard of, so it's a US company of Grok that is making inference-only accelerators. So there is, they show that there is a market for hardware which is less complex than the GPU. They could be done by a medium company. They don't need to be the big NVIDIA or big Intel or big AMD. So there might be a market here for more inference that could be surrounded. And here, indeed, a collaboration between Europe and Japan could be a good way to go onto in this direction. But of course, we need the willingness, the policy, and things like that, so, of course.
Thank you very much. Any additional comments?
I would also add that you need to be strategic about the kind of infrastructure needs of your AI strategy, because a lot of countries have dedicated AI strategies where they line out what they want to do in the next couple of decades. But in very few instances do countries even know the compute resources that are available in a country. So there are only a handful of countries that have done a dedicated compute review, or like an AI compute review, even more in detail, to understand whether they have the capacity to do what they actually lined up in their strategy. And that is really helpful, because if you don't have that kind of strategic view on infrastructure and the energy needs and maybe the availability of renewable energy, then you run into problems like what Ireland has experienced, what Singapore has experienced, where they had to do a full moratorium on new data center development because the additional data centers that were planned were kind of in a complete overcapacity. The grid couldn't handle any new data centers anymore. So you need to think about it strategically, and it is becoming critical infrastructure. And like think about all the different parts of that life cycle, and energy is one of the most crucial parts. So in order to be able to plan that, you need to have a strategic overview on a country level, or maybe even on the European level, to be able to continue to build out that infrastructure.
Thank you very much. If I may proceed with a second question, which I think may have perhaps a straightforward answer. We've entered the age where multimodal models are becoming more common, processing text, images, videos, and so on. How does this affect energy consumption? And how is this maybe balanced out with efficiency gains we heard of, or developments in hardware?
So again, multimodality is demanding different way of processing, but here you have a demonstration of video processing in real time with very low energy. So with some pre-processing done by such a chip, so this could be a chip. So I'm more thinking about the usage for autonomous car using LLM, or for robots or things like that. So I think this will be the next generation. So processing your image on your laptop, it's good enough, it's encoding and goes to the cloud, but really going to the next generation, so that's having a generative AI that could see, that could hear, that will need a more dedicated hardware, but we are going on this track as well. So this is ongoing. So the core of the processing, so the training and things like that, it's still more traditional, but all the multimodality in real time, research laboratory are already working on this. So yesterday we have a session on robotics, and on robots could benefit, of course, of this without needing a big GPU, which is the current limitation of the robotic actions. But of course, hardware development goes after that algorithm and the need is present. So this will happen in the coming years. So even if this need is today.
Thank you very much. a question that perhaps might be best answered by Professor Yokota, also because you talked about sharing information, data transparency with regard to research. How do we prevent overproduction of redundant AI models, sort of duplicating efforts in different countries? What role does international collaboration and decentralization play against this background?
So yes, I think there are different ways we can collaborate and different things we can share. The easiest things to share are these anecdotes or the failures that we have each experienced. This does not require exchange of sensitive data, nor does it require any exchange of the key technologies. It just, basically sharing our experiences is something we can easily do. So this, I think, should be done more frequently amongst our different consortium. So there are many different groups, but they meet very infrequently, and all these consortia, international collaborations on AI are somewhat medium to small scale, and there's no comprehensive effort to basically share all this information. So maybe everyone training above a certain scale, if they could just share their basic information, there could be a platform where they could post the configurations they use and what happened with those configurations. Fortunately, most of the researchers in academia are doing this openly, so they are willing to share this information. The industry is a little bit different. There are certain things they cannot disclose, even if it's not their data or their model. Even their training configurations, sometimes they're hesitant to disclose. But I think there could be some middle ground that we can strike. And the more we can share, the more we can reduce these redundant failures that are happening. So yes, I hope we can move in this direction.
Thank you.
Can perhaps add a personal opinion. I think in the scientific community and in conference, there is also the way to show what is working. And it's very difficult to present a paper showing that this is not working. So and when I was in industry, they say that the failure is more important than the success, because you know what you should not do and repeat in the future. So perhaps we should set a conference on what is not working on neural networks. So that could be perhaps quite useful also to share of all this kind of problem we have in training, and not only showing the paper with the success. So that's a personal opinion.
I think this is maybe also a wonderful way to conclude the session. And unless Professor Kirnberger, you had anything to add?
Just to double down on the need for transparency, especially from the private sector, and of course that's difficult because a lot of that is kind of proprietary information and that's trade secrets. But at the same time, because also the balance of who has access to the most cutting edge compute is shifting a lot into the private sector, that just emphasizes the need for transparency, and you see some movements in that direction. But like especially for being able to judge whether something is actually like how sustainable certain models are, there is an urgent need for transparency and comparability. Not saying that because the OECD likes to compare and standardize some things, but because that's genuinely, I think we've seen it today, that in order to give like not just anecdotal evidence, but to actually compare it, you need that kind of transparency.
Yeah, thank you very much. That's actually an additional very good way to conclude this session. I think there still are quite a number of very interesting yet open questions relating, for example, to measuring energy consumption. You outlined that. I think there's also an interesting issue relating to the sustainability of proprietary models and against the background of fostering transparency, collaboration, openness about models. We still have time today for discussions, so perhaps you can pick up on these questions later on. I was asked to thank you very much. A big round of applause to our speakers and the chair. I was asked to direct you rather rapidly to our next session, and I was told actually that you have time to grab a coffee. I don't know whether we now have coffee outside, but please do check.